Hello friends, let us resume our discussion on understanding certain fundamental concepts of thermodynamics and thermodynamics as a whole. Now in the previous lecture, just to have a recap of what we saw in the previous lecture, we began by considering the Newton's laws of motion. So this is something that will help us establish a common ground. We began with that, and we saw that in Newton's laws of motion, when we want to study the Newton's laws of motion, there are certain considerations that we render. That is, we begin with an object and we assume that this object is present in a specific condition, and we saw this condition can be static, that is, it is not moving, this particular object is not moving, or this condition can also be moving condition, or it's a dynamic condition. So in order to describe this condition, we need to introduce certain variables, and the reason why Newton's laws of motion is a good starting point for thermodynamics is primarily because before the conception of the field of thermodynamics, when dealing with a behavior of an object be it static or an object that is in motion, while discussing about this behavior of the object, the concept of energy was not largely associated with it. The concept of energy was dealt in a separate realm, while this behavior of the object, be it in static condition or be it in dynamic condition, it was dealt in a separate realm. It was dealt as a separate topic. Now whatever factors that governed these different conditions of the object, they were dealt separately in the framework of Newtonian mechanics. However, it was soon realized that the factors that is used in the Newtonian mechanics, which ultimately help us understand the work done on an object, the works that is done on an object or work done by an object. So these factors, it include force and displacement. So these are the different variables that are largely used in the Newtonian mechanics and mechanics in general. So now it was realized that this work, they produced energy. So it means that the work and energy, they are interrelated, and because of this understanding, because of this observation, it was soon realized that it was thought that both these work and energy can be studied in a single framework. And this framework is what we now refer to as the thermodynamics. So originally, work was treated in a separate realm, and the forms of energy was treated in a separate realm. And because it was realized, or because it was observed that the work at times, though wanted or unwanted, it yielded some amount of energy, it came to it then dropped on us that the work is associated with energy. And that's the reason we want to study it in the single framework, and that framework is the thermodynamics. Now, once we have established this thermodynamics, then we have certain characteristic terms or certain characteristic terminology we need to understand in order to discuss the thermodynamics of a specific system. So what we call as object, what we refer to as object in the Newton's laws of motion, we saw that here in the field of thermodynamics, in the realm of thermodynamics, we refer to that as system. The reason we have this distinction in names, because the consideration that is rendered to object and the consideration that is rendered to the system in the framework of thermodynamics is quite different. And that's the reason we need to distinguish the object from the system, and that's the reason why we have a separate terminology and we don't adapt the same terminology from the Newton mechanics. So we have a separate terminology, and that terminology is system. So what system is in the framework of thermodynamics is that the system is a region of interest, our interest. So we want to study a specific, not the entire universe, and even if you want to study the entire universe, then this entire universe would be the system. And we need to have something that distinguishes the system from the rest of the surroundings. So essentially in thermodynamics, we have a region of interest, we refer to that as systems. And in order to distinguish this system, that is the region of interest, from its neighbors or its surroundings, is the rather a common word, and you can directly associate with it. So in order to distinguish this system from the surroundings, you have a boundary. Now depending on the nature of this boundary, you can categorize your system, or you can describe your system in a different or wide range of ways. And in the previous lecture, we explicitly did not get into the details of what are the different forms of boundaries that are available, or what are the different forms of boundaries that we can consider, and how correspondingly the name of the system would change. That we did not explicitly consider. The reason primarily is because while facing a specific problem, while facing or discussing a specific aspect of thermodynamics, I thought in that context, explaining the nature of the system or the nature of the boundaries that allows for this particular system to exist. So in that context, it will give you a clear understanding. So discussing just exclusively on the different natures of boundaries and the system, I thought it would be rather distinct. So that's the reason why I want to introduce the different systems and the boundaries while we are considering or addressing a specific problem. Now we saw that once you have established your system, in case of Newton's laws of motion, you had to establish an object and the condition in which the object existed. Now in case of the equivalence of the same framework or same setting in the thermodynamics is a system and its state. So we saw like an object and its condition in the Newton's mechanics, we have system and its states in the thermodynamic. Now in order to describe the state of the system, there are two different approaches that we can adapt. One is understanding the microscopic states of the entities that constitute a state or rather a system. So we have a system and this system comprises of entities and we can consider the behavior of these entities and then we can combine all this behavior and then describe ultimately the state of the system. That is one way of going about and that is referred to as the microscopic, and this individual behavior or the individual condition of these entities can be referred to as the microscopic state, and then we can combine this all together and ultimately describe the state of the system. Now we saw this approach is possible or this approach is valid because when you break down your system into smaller pieces, you get down to the level of atoms. What ultimately involves there is the Newton's laws of motion. So you can describe the state of the system again from the Newton's laws of motion because you have atoms that are working that are behaving in accordance with the Newton's laws of motion. So again your Newton's laws of motion comes into thermodynamics in the microscopic state, and then based on that you can describe the state of your system. But unfortunately for us, this being a thermodynamic, exclusively a thermodynamic class, we won't be taking that approach because it needs too many variables. When you consider individual entities, their behavior, too many variables are involved. And again, this being an exclusively a thermodynamics approach, we introduce different variables that does not consider the individual entities of the state, but the state as a whole. So this allows us to introduce or treat the system as a whole in a macroscopic scale. So as opposed to the microscopic consideration, the thermodynamics often treats or most always treats the system on its macroscopic scale, and in order to describe the state of the system, it introduces its definite variables, and this using this variable we describe or define the state of the system. Now the reason why we are able to introduce or describe a state of the system on a macroscopic scale using a specific set of variables is because when you fix these variables, when you fix these variables that you use to describe the system, when you fix them, the state of the system is fixed. So this allows us to describe the state of the system using these macroscopic variables. So when you fix certain variables, the state of the system is fixed, the condition of the system is fixed. So when I mean condition, even the macroscopic even the microscopic state is fixed. So when you have such variables, then we can use that variables to describe the state of the system, and those variables are called as thermodynamic variables. Now again, in order to establish some sort of a relation, we went back to the Newton's laws of motion, wherein even there are several variables that are involved to describe the conditions of an object, and we saw that even those variables can be distinguished into dependent and the independent variable. We saw in case of Newton mechanics, we need to understand the position of an object, and we need to know with respect to time, and once we have the understanding of the position of the object with respect to time, then it will be possible for us to predict the velocity of a moving object, and also if the object is moving at a different velocity, it is possible for us to determine its acceleration. So essentially what we have is, even in the framework of Newton's laws of motion, the variables that are involved or that are used to describe the condition of the object can be categorized into dependent and independent variables. In the similar way, the thermodynamic variables that help us describe the state of the system, that help us fix the state of the system, can be categorized into dependent and independent variable. So the reason we need to categorize the thermodynamic variables into dependent and independent variables is primarily because when we want to describe the state of the system, ultimately on a physical scale, on when you are doing some experiments, or when you want to understand or describe the state of the system, you tend to measure these thermodynamic variables. Now, when you distinguish these thermodynamic variables into independent and dependent, so supposing the combination of these two rather gives you 10 different variables, and now you are able to distinguish into 3 independent variables and 7 dependent variables. This distinction helps us understand which variable needs to be measured. So measuring each of these variables will not be a simple task when you are considering an experimental setup. Now this distinction helps us measure or focus on the specific independent variables, so that once we know what these independent variables are, from that we will be able to calculate the dependent variables. So that is the reason why we distinguish the thermodynamic variables into dependent and independent variables. Now let us consider a simple example to understand what are these different dependent and independent variables appear, and how these dependent and independent variables appear, and how we can play around with them to make our whole study of thermodynamics rather simpler. So ultimately, the study of thermodynamics, even though it is largely theoretical, it needs to have a physical significance, a physical attribution to it. And one of the physical attribution, to make that physical attribution rather straightforward, to make it not too difficult, this connection between the theoretical thermodynamics and the practical aspect of it, to make it rather simpler, we make this distinction and we rather play around with this dependent and independent variable. So let us consider an example and see how we can work with this dependent and independent variables. Now, this is rather again a straightforward. This is a very straightforward example, and the one you might have come across maybe in your school days or even in your bachelor's course. So essentially, what we will be considering is a system of a small system which comprises of compressible gas. So we are considering a system that comprises of a compressible gas. Now this system is a closed system. So the molecules of gas, the atoms of gas is not allowed to get out of the system. However, the temperature or the heat is allowed to pass through this system. So in or out of the system, the temperature is allowed to pass through. So in or out. And similarly, you can impose a pressure on this system. So you can, in this system, what you can essentially do is, only a restricting factor of the system is that in this system, the molecules of the gas are not allowed to go out. However, apart from that, you are allowed to allow the heat to transfer. So the temperature change is allowed to happen, and you can impose work on the system. You can work on the system can work on the surroundings. Now, when you consider such a closed system and you begin to impose a pressure on this system. So this being a compressible gas, you begin to impose the pressure on the system. What ultimately happens is that the volume of the system changes. So again, this is something that you would know. So as your pressure increases, the volume of the system, it decreases. So this we refer to as the generally as the Boyle's law. Now, by imposing the pressure, you are ultimately reducing the volume of the system. Now, instead of imposing the pressure, now here the only variable is the pressure, and because of the change in the pressure, there is volume that is changing. And in the second condition, you assume the pressure to be constant. So pressure is constant, and now you increase the temperature of your system. Now when you increase the temperature of your system, the kinetic energy, now we are going to the framework of Newtonian mechanics, the kinetic energy of your individual atom, they increases, and because of this increase in the kinetic energy, these atoms impinge on the walls of or the boundaries of your system, and therefore they increase the volume in order to reduce the kinetic energy and to reach a stable state. Now in that case, so increasing the temperature would correspondingly increase the volume of your system. So here the pressure is assumed to be constant, and here the temperature is assumed to be constant. this is nothing but the Charles law, and this is Boyle's law, if I'm not wrong. So what essentially we have is, we have pressure that is governing that is influencing the volume, and temperature that is influencing the volume as well, and there is a constant proportionality that is involved in both these expressions. Now we can write both these expressions in a way that both variables are included in the same framework. So when you take club this together, you have a direct proportionality, and then you have you have an inverse proportionality, and you have a direct proportionality. You can write, so you have a common parameter for a variable here. So this V is proportional to T by P. So essentially what happens is, the volume increases with temperature and decreases with pressure. And now when you can rearrange it, and PV by T is a constant. So this relation here is a constant. Now essentially what this expression means is that, so you have three variables that are related to a constant. So you can keep one variable on your left hand side, move the other two to the right, and thereby establishing a relation between one variable and the other two variables. So you are essentially creating a relation between two variables and one variable. So essentially what is happening here is, one variable is dependent on two other variables. So this is what we mean by dependent and independent variable. So this is not restricted to rather pressure or volume or temperature. So this is just an expression, this is just a law that is observed in gases, and based on this law we were able to extract this relation. And when you treat this relation purely from a mathematical perspective, then it is possible for you to consider any variable as a couple of variables as dependent, and the other variable, or any couple of variables as independent and the other as dependent. You can treat rather pressure as the dependent variable, constant into rather T by V. So you have your constant and this relation here, and you can treat any other variable as the dependent variables, and the rest, or the other two variables, as independent variables. The reason why this is important is because the reason of this flexibility is important, even though based on the expression, based on the law, it is very well clear that it is the volume that is a dependent variable. The reason it is important for us to play around with this dependent and independent variable, to consider one as the dependent variable, the other as the independent variable, is because when you relate your thermodynamic understanding to a physical setting, at certain setups it is easy for us to measure certain variables. For instance, in a setup it will be easy for you to measure temperature and volume rather than the pressure. So in that case it will be favorable for us if you treat temperature and volume instead of pressure, and temperature and volume as the independent variable and pressure as the dependent variable, instead of the classical consideration of volume as the dependent variable. So the reason we need to consider the whole of the expression that includes both dependent and independent variable, the reason we need to have this freedom of treating the desired variables as the independent variable, and the variable that is difficult for us to measure as the dependent variable, it helps us approach, or it helps us translate the thermodynamic understanding to a physical setup. Again, to reiterate, when you have an experimental condition wherein it is difficult for you to measure the pressure that is acting on the system, then it is possible for us to measure or consider or treat the temperature and volume as the independent variable, measure them, and from that calculate the pressure. So even though classical, so it is something that you need to carry on or carry over to other subsequent lectures and understanding of the thermodynamic variables, particularly when you want to use the thermodynamic variables to every experimental setup, you need to know that it is possible for us to choose from a given set of variables the independent variables and the dependent variables. So depending on the experimental setup, the physical setup you want your thermodynamic understanding to relate to, you can appropriately select the independent variables and the dependent variables. Now we have seen these variables, the thermodynamic variables, can be categorized into dependent and independent variables, and once you established a formulation wherein all these variables are related, it is possible for us to select a set of variables as independent variables and another set of variables as dependent variables. This selection can vary depending on the settings you consider. For a setting wherein measuring temperature, or you can also have a setting wherein measuring volume and pressure is rather straightforward. So in that setting, and all these are varying, then in that setting it is possible for us to assume pressure and volume as the independent variable and temperature as the dependent variable. So this is one way of distinguishing or categorizing the thermodynamic variables into two. So that is dependent and independent. So there is also another way of categorizing the thermodynamic variables. So in order to understand this categorization of the thermodynamic variables, again let us focus on this expression we have here. So this expression we have in this this particular expression, that is PV by T is a constant. So this expression allows us to understand one concept that we saw in the previous lecture. So the one concept that we understood in the previous lecture was that when you have a system and when you are describing the state of the system using a specific set of variables, it means that using this set of variables you are able to fix the state of the system. We saw in the when we wanted to recap what we saw in the previous lecture, that when you describe a state of a system using a specific set of variables called thermodynamic variables, the reason we are able to call this as thermodynamic variables because we can fix the state of the system by fixing these variables. Now that understanding can be gained from the expression that is written here. So this expression that relates pressure, volume and temperature, from this we can see that by fixing the variables we will be able to fix the state of the system. Now let us for the sake of the understanding stick to the system that we have in our hand, this open system that wherein we are allowed to introduce pressure and the temperature is also allowed to enter into the system. Now in such a system, the state of the system is defined by these variables. So we have our pressure that is allowed to enter into the system and that is allowed to change within the system, and we have defined our system or constructed our system in such a way that the temperature is also allowed to introduce into the system or go out of the system, and it is allowed to change, and then correspondingly we have a change in the volume of the system. Now we saw that there is a relation between these three variables that helps us categorize these set of variables into dependent and independent variables. Now in addition to categorizing the dependent and independent variable, the nature or the state of the system can be fixed by fixing the independent variable. So what we mean by that is, if I fix my temperature, say T1 at T1 and my pressure at P1, then correspondingly because of this expression here, what happens is my V1 is also fixed. So when I fix, or when the temperature of the system is set to T1 and the pressure of the system is set to P1, so because of fixing these two independent variables, now I am able to fix the volume of the system. So ultimately by fixing the independent variable, the state of the system which is defined by these set of variables is now fixed. And we are not fixed the state of the system by considering or fixing each of these variables, but just these two independent variables. So the reason why we were able to fix these the entire state of the system by fixing the independent variables is because there exists a relation that relates all these three variables. So the volume is dependent on these two variables. So this expression helps us understand that for a given combination of temperature and pressure, there is a specific volume that is associated with the system. So we have considered a specific form of a system, and in that simple system, in that closed system, we consider a specific temperature and pressure, and for that specific consideration of temperature and pressure, you have your volume fixed. So you have your temperature fixed, pressure fixed and volume fixed. Ultimately you have fixed the state of the system. So for a given temperature, pressure, the state of the system is fixed. So ultimately you have your system that is represented by P1, T1 and P1. So you are fixing the state of the system by fixing the independent variables alone. And more importantly, for a given combination of pressure and temperature, your volume of the system is fixed. Now graphically, this can be represented by considering the pressure and the temperature along the x and y axis respectively, and volume along the z axis. So you have your pressure, you have your temperature and volume. Now this is now when I fix my pressure and temperature P1 and T1. The volume is fixed and that will correspond to P1. So the state of the system is fixed. When I mean the state of a system, it means I have fixed pressure, fixed temperature and correspondingly fixed volume. Now this state will not change unless otherwise I change these variables. So I can either change, so in this consideration or in this setting we are considering pressure and temperature as the independent variables. So under this setting, this particular volume of the system, which ultimately describes the state of the system, will only change if I either change pressure or temperature or both. Only when I change the independent variables, the state of the system changes. So in order to change the state of the system, I need to change the independent variable. So such a condition wherein the system remains unchanged unless otherwise the variables that describe the system changes is referred to as the equilibrium state. So equilibrium or the stable state. So I might use these terminologies synonymously. So what we mean by equilibrium state or a stable state is that when you have a state of a system that is described by a specific set of variables, and this state of the system only changes when you change this variable, it remains as it is. If you don't change the variables, then what you essentially have is a state of the system that is in the stable condition or in the equilibrium condition. So in order to change this state of the system from its equilibrium condition, essentially we need to change both pressure. You can change either pressure or temperature or both. So you can disturb your system which is in the equilibrium only when you change the variables that describe that particular system. Now let's try to change both pressure and temperature together. Instead of considering a system, say V1, which is defined by P1, T1, let us move the system from, or let us change the pressure and temperature to say P2 and T2. So when I change the pressure from P1, T1 to say P2 and T2, what essentially happens is that the corresponding volume also changes. So let me use a different color. So here we have moved from P1, T1 to P2, T2, and correspondingly the volume of the system changes, and now it has moved from one equilibrium state or one stable state to another stable state, primarily because we have changed the independent variables. So we have now a different volume, a different state of a system that is described by the combination of V1, V2, P2 and T2. So we have a different sets of temperature, pressure and volume that now describes your system. It is please note that the variables, they remain the same, but their quantity changes, and therefore we have a different state now. And this state again is in equilibrium because when you want to move the position of your system from this state, from this green state back to any other state, you again need to change P2 and T2. So it means that your system again is in the equilibrium condition. Now what we can do is we can try to see what is the change in the volume when we changed our variables or the independent variables from P1 to P2 and T1 to T2. So the change in the volume is nothing but the final volume minus the initial volume. So essentially this is the difference between the change that occurs in the system, the visible change that occurs in the system, that is the change in the volume, can directly be described by V2 minus V1. So essentially there is a change in the pressure and the temperature, and because of that you have a change in the volume. So the state of when you say the volume changes, essentially the state of the system changes, and this state of the system is described by or visible to us in terms of the dependent variable in the form of volume. So this is the difference that we see when you change the pressure and temperature. Now similarly, the change in the pressure can also be expressed as P2 minus P1, and the same goes for the change in the temperature. So change in the pressure, change in the temperature, and ultimately the change in the volume is just nothing but the difference between the corresponding values in the initial state and or rather the difference of the corresponding value in the final state and the initial state. So these variables even though they change from one state to another, the difference is nothing but this change that they exhibit is nothing but the difference in the value we assume in the new state minus the difference in their original value. So this is how we see or we quantify these change in the state. The difference in the state is quantified in this manner, and because this variables or the change in this variable can be measured or can be quantified just by considering the two different states of the system, by considering the difference between the two different states of the system, these are referred to as the state variables. Now what we have seen is, we have seen that there are certain variables that help us fix the state of the system, and these variables rather, when you change them, the state of the system changes. And now when you want to compare these variables in these two systems, you have a green system and you have a red system here, you have your green system and you have your red system here, and when you want to compare the change in these variables, when the state of the system changes, all you need to do is subtract or consider the difference between these variables in the corresponding system, and you end up on you are able to quantify this change in the variables. And that is what, and because of this behavior, we refer to them as the state variables. Another way of looking at it is, the state variables are the set of variables that help us describe the state of the system. So when you have a system in a specific state, and you need to describe the state of the system for this system of a particular boundary that is associated with it, then you need a specific set of variables. So you are not considering the history or how the system came into this particular state. We are not worried about that. We are just considering the state of the system, and you are trying to describe the state of the system. So whatever variables you would consider just to describe the state of the system without giving thought to what is the history behind it or how this system came into this particular state, these are referred to as the state variables. So there are two ways of defining a state variables. You can consider two different perspectives of defining or categorizing or identifying a state variable. One perspective is that you consider the change in the state of the system, and you see how we can quantify how when the system changes from one state to another, how the variables associated with that changes. So when you do that, when this change in the change in the variables is just the difference between the variables of one particular state and its previous state, then that particular variable is a state variable. So that is one perspective. This perspective, the first perspective, it just considers the different states of the system, and it wants to identify how much a given variable has changed. When the way of identifying how much the given variable has changed is just taking the difference between the two different states, then that particular variable is the state variable. The other way of looking at it, this approach, it considers two different states. Now the other way of looking at the state variables, so other way of categorizing or identifying or realizing a state variable is that you just consider a state of the system. You don't worry about its history. How did this particular, so you just consider this state of the system here. You don't worry about where it came from or how it came into being or how this particular state of the system, alright? You don't worry about all those things. You just focus on this particular state, the state that is now stable, and now you want to describe the state of the system and all the variables that are required to describe a given state of the system without worrying about its history. Those variables are also or can also be referred to as, or they are referred to as the state variables. Now we have seen three different variables. Unfortunately for us, these three different variables are state variables because their difference is what we need in order to see how this variable changes. And even if you want to consider this given state of the system, we need all these three variables, or we need at least the two independent variables to describe this state of the system. So the bottom line is, when you see a set of variables, you can distinguish these variables into state variables and the other set of variables. The other set of variables we will eventually get to. So we can distinguish these set of variables by, there are two ways of doing it. One way is to consider two states of the system. If you don't know the two states of the system, all you have is just one state of the system, a given state of the system. Then the way of identifying the state variables in the given set of variables is, you have to ask the question, if this variable, if understanding this variable needs any understanding of the history of the system. If in order to describe this variable, in order to talk about this variable, do I need any understanding, any pre-knowledge of what happened to the system or what will be happening to the system? If such a consideration is necessary in order to describe a variable, then that variable is not a state variable. When you see a set of variables and there are some variables which can directly be used to describe the state of the system, those variables can be the state variables. Now that the state variables are particularly when you define your system based on the state variables, and when your system moves from one point to another point, it just depends on the change in the system can be quantified by just considering the difference in these variables. It helps us, particularly from a thermodynamic perspective, to disintegrate or fragment a given understanding, a given change in the evolution or change in the state of the system into smaller pieces. Let me repeat, when your system is exclusively defined or described by state variables, and this state variables means, or what is the characteristic feature of the state variables is that when a system changes from one state to another, in order to quantify this change, all you need to do is consider the difference between these variables. You need not worry about the way these states have been achieved. Because of this characteristic feature of the state variables, it allows us to break down a given change in the state of the system into smaller pieces. So let us see what it means in the simple example that we have considered. So we have seen that, again, let us consider a setup like this. We have our pressure, we have our temperature, and we have our volume here. Now we have seen, let us assume that the initial state, the red one is here, that is P1 and T1, and there is a final state, that is here P2 and T2. So because of by fixing P2 and T2, we are ultimately fixing the volume, and by fixing rather the temperature and pressure in the initial state, we are ultimately fixing the volume there as well. Now the change in the initial and the final change in the system can be quantified as V2 minus V1. Now because V2 and V1 are the state variables, we are able to calculate the overall change in the volume of the system in this manner. Now supposing instead of directly moving from V1 to V2, we are taking a V2 and we are taking a path in such a way that instead of going directly, we take an intermediate step here, which is VA, that comprises of, that is described by PA and TA. So we have a detour. We take a detour. Instead of directly going from V1 to V2, we move away from this direct route. We want to go to VA and then go to V2. So instead of moving from V1 to V2 directly, now we want to have moved from V1 to VA and V2. Now this V1 is associated with P1 and T1, PA and rather TA, and V2 is P2, T2. Now, so we have, instead of the system changing its states from V1 to V2, we have two changes, that is from V1 to VA and then VA to V2. Now let us see what is the volume change that is associated with the first change. So let us assume this is to be the first change. So delta V of the first change is nothing but PA minus V1. So because again this volume, the volume is a state variable, the change in the state is nothing but the difference. So we have an initial change in the state, that is from V1 to VA. So this change in the volume for this first set of change, that is V1 to VA, can be expressed as, so the first set of change is represented by this numerator here, and it is nothing but the difference between VA and V1. Now in the second set of change, the change in the volume, in the second set of change, wherein your VA, after the V1 reaches to VA, it moves to V2, this change is referred to as, or this change can be quantified as V2 minus VA. Now the overall change, delta V, that we have seen here, the overall change in the volume of the system can be referred to as this change in the volume during the first set of changes, or the first set of the change, plus the change in the volume during the second set. So essentially the entire change in the volume we have broken down into smaller pieces. The first change is between V1 and VA, the second change is between VA and V2, and now we have quantified the change in the volume for each of these changes, and this is what we have expressed here. And now we have to calculate the overall volume, and when we do that and introduce this term, we will observe that these VA terms will get cancelled, and we will ultimately end up with this expression here. So what this states is we can realize two things from this simple thought experiment. So when you add a step between two different changes in states, so you have a change in state from V1 to V2, you break that continuous change into, you take a detour, you add an additional step to it, and then you consider the change in the state between these V1 and VA and VA and V2. So instead of considering one change in state from V1 to V2, you then break down into V1 to VA and VA to V2 as change 1 and change 2. Even after doing that, when you ultimately calculate the overall change in the volume, you observe that it is like we have considered just the change in the system from V1 to V2. So ultimately the overall change in the volume is just defined by its initial state and the final state. The intermediate state is missing. So this again substantiates our definition of the state variable. So irrespective of the number of detours you take, irrespective of the number of intermediate steps you take, when you have an initial state and the final state, the difference in the state of the system, particularly when it is exclusively when it is being described by the state variables, is nothing but the difference in the initial state and the final state. So this is one of the characteristic features of defining a state of the system using the state variables alone. So this is possible exclusively only when you define the state of the system using state variables alone. So under such a condition, irrespective of the number of steps that are included in between, irrespective of that, you will be able to define the overall change in the state of the system based on the initial and the final condition alone. The overall change will be the difference between the initial state and the final state. Now this is again, we saw that one understanding that we can gain from such a consideration of adding an additional state between two initial and the final state. One understanding that we can gain from it is that you can add n number of steps in between. We have just considered one. We can add any number of steps. You can add another intermediate system here. You can add another intermediate system here, another intermediate system here. So instead, irrespective of how many intermediate systems you consider, how many intermediate states you consider, wherever it might be, once you have an initial and the final state that are described by your state of the system, then irrespective of these intermediate states, you can define the initial and the final state of the system and the difference between them just by considering the initial state and the final state. You can define or quantify the change in the variables from the initial state to the final state just by considering the difference in the appropriate or respective values of these variables in the initial and the final state. So it doesn't matter how many intermediate states you include. Now, because the state variables allows us for the inclusion of the several intermediate steps, we can describe our thermodynamic problem, our given change in state, in a simpler way. So what I mean by that is, this all stems from the characteristic features of the state variable. This is something you need to understand. Because our system is defined by the state variables, and state variables allows us a system that is exclusively defined by or described by the state variables, allows us to introduce any number of intermediate systems without disturbing the initial and final consideration or initial and final state. We can break down any given change in the state into smaller fragments that is convenient to us. So what I mean by that is, the change in the state of the system from V1 to V2, it involves both change in temperature from T1 to T2 and pressure from P1 to P2. So when you consider the change in state directly from V1 to V2, so there are, let's say, a direct change from V1 to V2, what essentially is happening is we are simultaneously changing temperature T1 to T2 and P1 to P2. In order to achieve a change in the state of the system directly from V1 to V2, we are changing both pressure and temperature to one value to another value. Now, since this understanding, so this theoretical consideration here has helped us understand that when your system is exclusively described by state variables alone, it is possible for us to consider any number of intermediate states. We can, instead of treating this V1 to V2 as a single change in the state of the system, we can consider V1 to VA and then VA to VB and ultimately V2. And this initial change in the state, we can assume during this initial change in the state, the temperature is constant, and during the this change from VA to VB, the pressure is constant, and ultimately we can combine these two states and render the V2. So essentially, or an even more accurate way of putting it is, so we just can introduce an intermediate step wherein the initial change, during the initial change, the temperature is constant, and from the intermediate to the final state, the pressure is constant. And by introducing such or breaking down the entire change in the state of the system into smaller fragments, or introducing an intermediate step, instead of considering the change in both variables temperature and pressure together, we can consider a setup wherein only one variable changes. So here from V1 to VA, we assume that the temperature is constant, so therefore only the pressure changes in order to bring a change in the volume from V1 to VA. And in the second change, we assume the pressure to be constant and only the temperature changes. So what essentially we mean by that is, what the system exclusively defined by the state variable help us do is, it helps us break down an overall change in the state of the system into smaller fragments, and these smaller fragments can be defined according to our convenience. So here, instead of treating the change in the system by simultaneously changing both the independent variables, we can break down this overall change in the system into smaller pieces, wherein we assume the first piece, the temperature is assumed to be constant, and in the second piece of the change, the pressure is assumed to be constant. So this helps us to handle the change in the state of the system in a more elegant manner, in a more rather an easier way, instead of explaining. So far we are not gone into any expression to describe the change in the state of the system, but when we get into it, you will understand that this way of breaking down a change in the state into smaller fragments help us express this change in the state in a more simpler way. So this is possible because we have defined our system exclusively based on the state variables, and these state variables, these states of the system, they will not change even if you add some intermediate steps. So we will build on this understanding in the subsequent lectures to help us appreciate how introducing the intermediate states help us simplify the expression for the change in the state of the system. Goodbye.